Cayley, Jerome, and Farzad write a test independently. The probability that Cayley passes the test and Jerome fails is 3 over 20. The probability that Jerome passes and Farzad fails is 1 over 4. The probability that Cayley and Farzad both pass is 2 over 5. To determine the probability that at least one of Cayley, Jerome, and Farzad fails the test. Well, let's make a little table. We have Cayley, Jerome, and Farzad, and the probability of pass and the probability of fail. So let's see if we can convert the sentences in the question to this table. Okay, so the first sentence, probability that Cayley passes and Jerome fails. Oh, this is a double. Oh, I thought it was a little bit more simple than that. Okay, so let me just use some letters here. Let's call this A, let's call this B, let's call this C. This would be 1 minus A, this would be 1 minus B, and this would be 1 minus C. Ooh, okay. Well, we all know that the probability of something is always going to be between 0 and 1. You guys already know that. I just wanted to write it down. And what else do we know here? I guess I just have to write it out. It's not as straightforward as I initially thought. Okay, so the probability of Cayley passing, so A, and the probability of Jerome failing, so that's 1 minus B, is 3 over 20. So if A is some number, usually it's probably a fraction, and it's the key is and, we have to multiply by the probability of Jerome failing. So that's 1 minus B. So A times 1 minus B is 3 over 20. Okay, so that's I think how we're going to do this. And then of course we can always, use algebra to get everything in terms of one variable, but that'll be used a little bit later. Okay. So let's move forward. The next one is Jerome passes and Farzad fails. So Jerome passes is B, and Farzad fails is 1 minus C. And that is 1 over 4. So that means A times 1 minus C. Hold on, not A. B. Got to make sure I get my letters correct. B times 1 minus C is 1 over 4. Okay. And then, of course, whatever algebra you want to do, B is equal to 1 over 4 times 1 minus C. Okay. And then the last sentence, Cayley and Farzad both pass. So Cayley and Farzad both pass. So that's the probability of A happening and C happening, right? And they're saying that is 2 over 5. So that's basically A times C is 2 over 5. Or A is equal to 2 over 5C. Okay, that's actually a very good start. And now, what do they want me to do here? The probability that at least one of them fails. So the probability, hold on here. The probability of at least one failing. At least one failing. Okay, so if they all pass, let me just write it here. Probability of at least one failing, is that right? Yeah, is equal to the probability of 1 minus all of them passing, right? Because at least one fails means 1 fails or 2 fails or 3 fails. It does not include all of them passing. So all of them passing would be a separate group or separate calculation. So this, I think, is the easier way. Let me just calculate this guy, the probability that they all pass. And if I can do that, then I'll be able to just subtract it from 1 to get the probability of at least one failing, which is what they want. So the probability of this guy, if you look at this table, would be A times B times C. So that basically means I have to get numerical values for A, B, and C. And somehow I have to do that with these. And I think it should not be too bad since there's 3 equations and 3 variables. It's just going to take some algebra. Yeah. So it shouldn't be so bad. So let me, I'm going to need obviously some space, so I'll just move it over. Okay, let's go for it. So our goal is to figure out the numerical values of A, B, and C, and then when I do, I can make that calculation. Okay, so here we go. A is equal to this, and A is equal to that, so let's set them equal to each other. That seems like a logical first step. So 2 over 5C is equal to 3 over 20 times 1 minus B. Okay, well, we still have 2 variables. We got C and B, but B is equal to this. So therefore, I could put that in. 20 times 1 minus B, and B is what? 1 over 4 times 1 minus C. Okay, so it's not the prettiest algebra, but it shouldn't be too bad. Okay, let's see what I can do. I cross multiply. If I cross multiply, I get 15C on this side, and I get 60 times 1 minus 1 over 4 times 1 minus C. Correct? Okay. And then what do I do now? Let me just expand this. Well, if I divide through by 15 I should say, this will be C and this will be 4. Yeah. And then expand, and we'll get 4 minus 4 over 4 over 1 minus C. This will be 1 over 1 minus C is 4 minus C. Is that right? I think so. Oh, sorry. I just noticed something here. It's a good thing I caught it. That's 2 times 20. Oh, boy. Yeah, I can't make those kinds of silly mistakes. That's a 40. Sorry about that. So it's a good thing I caught it early. So that actually changes things a little bit. That's not going to be a 4. That is going to be a 40 over 15, which is 8 over 3, actually. Boy. All right, sorry about that. So let's do the correct expansion. 8 over 3 minus 8. Well, actually, that'll be 2 over 3. Yeah, that's correct. Okay, so then that would be, we have to actually get this common denominator here. So 1 minus C, top and bottom. So 8 times 1 minus C minus 2. All over 3 times 1 minus C. So if you cross multiply, it'll be 3C times 1 minus C. And that's going to be 8 minus 8C minus 2. And this is 3C minus 3C squared is equal to 6 minus 8C. And let's put everything on one side. When you do, we get 3C squared minus 11C plus 6. Okay, very good. And does this factor? I think it does pretty decently. 3C, C, 2, 3, negative, negative. So C would be either 3 or 2 over 3. Now, remember, C is a probability, right? And it's a good thing I put that in there, right? Because that probabilities are between 0 and 1. So therefore, the correct answer for C is 2 over 3. All right, great. So then we just have to figure out the values for A and B, and we should be all set. So using these equations, we can figure out B, and we can figure out A. So B is equal to 1 over 1 minus C times 4, correct? Let me just double check, yeah. So when I plug in C is equal to 2 over 3, this guy, and you can calculate that, B will come out to 3 over 4. And similarly, A, which was 2 over 5C, when you plug in C equals 2 over 3, you'll calculate that A is equal to 3 over 5. So there we go. we got all the values, and then now we just have to go back and plug them in here, right here. So A is 3 over 5, B is 3 over 4, and C was 2 over 3. So this is going to be, let's see here, these cancel, this cancels, becomes a 2, so 3 over 10. Wait, hold on, 3 over 10. So then finally, we get this one. That probability would be 1 minus this guy, so 1 minus 3 over 10, which is 7 over 10. So all of that to get the final answer. The integer 7447 is a palindrome because it reads the same forwards and backwards. Suppose that positive integers m and n are palindromes between 1001 and 9999, inclusive with m greater than n. Determine the number of pairs mn for which the difference m minus n is a multiple of 35. Okay, so 7447 is just an example, right? So that doesn't need to be talked about. We have two additional numbers that are between 9999 and 1001, and they're telling me that m is greater than n. Okay, and they're palindromes. So since they're palindromes, they're going to be of the form like a b b a, and m, we'll just call it c d d c, correct? So this m minus n will be c d d c minus a b b a. Okay, and they're saying that's a multiple of 35. So 35 times something, let's just say 35k. And expanding this is going to be 1000c plus 100d plus 10d plus c minus 1000a minus 100b minus 10b minus a is 35k, right? So now I got to collect like terms here. Actually, first let me just do the math. 1001c plus 110d minus 1001a minus 110b is 35k, right? So then if I factor out a 1001, I'll get c minus a, and then if I factor out a 110, I'll get d minus b is 35k. And am I able to go any further? I don't think so. Let's see if these numbers can be factored a little bit further, because that might help. 1001 Well, let's see. 7 times 11 times 13. And then we have the c minus a. 110, that should be a little bit easier to factor. What was that? 10 times 11, so 2 times 5 times 11 times this d minus b. And then 35, as you are well aware, is just 5 times 7, and then that k. Okay, so all of that to get to there, and this is where the thinking now is going to start, because that's just basic algebra. But before I would tackle that, let me just go back and remind what all of these are. C, A, B, all that stuff, right? A, B, C, and D. And reminding these guys right here. What are those numbers? So A cannot be 0, right? Because these are 4-digit numbers. So A has to be between 1 and 9. That's important. B, however, can be a 0, so it could be between 0 and 9. C, similar to A, cannot be a 0, so it's going to be between 1 and 9. But D could be a 0, so that's between 0 and 9. Okay, so this is very important, these parameters here. That will help us. And this is also important. M is greater than n. So if m is greater than n, what does that mean? That means that C has to be greater than A. So C has to be greater than A because m is greater than n, right? I hope that makes sense. And I hope that's, is that true? Yeah, I'm pretty sure that's true. Okay. All right, so now let's go back and tackle this guy here. Now, all right, so let's work with this, see what we can figure out. Okay, so this is the heart of our question, I think, that equation. We have to kind of fiddle around. We have to try to get, things to match, right? We have all this equals to 5 times 7 times k. So this guy right here has to have similar factors as this guy. So how can we do that? There's, I think, a few scenarios here. I'm just trying to think, is this, how complicated this is. 1, 2, 3, 4. I think there might be able to do it with 4 or more, but I'm going to try to keep it in the same page here. I'm not sure how many there will be here. I'm trying to think. 1, 2, 3, 4, maybe 6, but I sincerely hope not more than 6, and then we'll keep a tally here. So at least I'll be able to keep it in the same page. All right, so here we go. Okay, so let's start with this guy right here. D minus B, this one over here. If you have D minus B, right? This is D minus B. If that was equal to 7, if that equals 7, then this could work, because then you'd have a 7 here. We're making that D minus B 7. There's a 7 here. And then everything has an 11. This is an 11 here and 11 here. And this could be an 11 or a multiple of 11. You see what I'm saying? So let's go with that. I think that's a pretty good start. So let's set D minus B equals 11. Oh, sorry, D minus B equals 7. And so that would make this 7 times 11 times 13 times C minus A plus 2 times 5 times 11, and then I'm setting that to 7, and this is going to be 5 times 7 times K, correct? So now we still have to talk about the C minus A. What can we get C minus A to equal? Well, C minus A, it could be 0, right? If it's equal to 0, then that would work. Or C minus A could be a common factor. So we have, let's see, 5, 5. We need a 5. We need it to equal 5. C minus A equals 5, yeah. And that would make it work. Okay, that's a good start. Okay, so let's go with that. So then we have to figure out how many possible ways can you get C minus A equal to 0, and how many possible ways can you get C minus A equal to 5. And that's where these parameters come in. So it's important to list those. C minus A can equal 0. Well, that would mean C is equal to A. And since there's 9 possible values for A and 9 possible values for C, that could happen 9 times. That could happen in 9 different ways. And then C minus A equals 5. That could make a quick table here. C and A, 9, 4, 8, 3, 7, 2, 6, 1. And I think that's it, right? Because you can't have 0. So there's 4 different ways that you can get for C minus A to equal 5. And then we have to figure out D minus B. How many different ways are there to make it equal 7? And I think for D and B, I can make a, I'm running out of space here, D and B, 9 and 2, 8 and 1, and 7 and 0. So 3 ways. Okay, that's a good start. So we either have D minus B equal to 7 and C minus A equal to 0, So that would be 3 ways to do that d minus b equals 7, and 9 ways to get the c minus a equal to 0. So that's 27. Or we have d minus b equal to 7 and c minus a equal to 5. So that would be a 3 times 4 scenario. So that would be equal to 12. Okay, so that's the first scenario. That's a very good start, I think. Okay, moving right along, let's go to the next possibility, which I think is d minus b equal to minus 7 and what else? And c minus a equal to 5. Before I continue, I'm just wondering if this is actually, I think it should be greater than or equal to, right? Because look, this is equal to, I just want to see, like, for example, if m was equal to 5, 2, 2, 5, if the c and the a are equal, yeah, you could make m greater than n, yeah. So that actually should be c is greater than or equal to a. Just wanted to make sure I made that one little correction there. Okay, getting back to this guy, the c minus a equal to 5, we already did over here. So there's 4 possibilities of making that. And then d minus b equal to minus 7. How many ways of there doing that? Well, let's see. Let's make a little table here. Let's see if we can fit it in. D and b, and we want d minus b equal to minus 7. So how many ways can we do that? D minus b, so 0 and 7, 1 and 8, and then 2 and 9. I think that's it. So there's 3 ways of doing that. And let me just make an example here. So going back to these definitions, if d minus b is minus 7, so m would be, let's just choose one. Let's choose this guy here. M would be something 1, 1 something, and then n would be something 8, 8 something. Now m is greater than n, so they could never be equal in that case. For example, if this was 5 and this is also 5, then m is no longer going to be greater than n. You see what I'm saying? So this would have to be, for example, 6, and that would have to be 6. Whereas over here, you could have a scenario where the c equals a. So if you had 5 and 5, and then we took one of these guys, so m would be, or sorry, we are taking not one of those guys, one of these guys over here, that c is equal to a. So then d minus b is 7, so let's take this guy. So the m would be c ddc, so it would be c, which I've chosen as 5, d would be 8, and the n would be 5, 1, 5. Yeah, therefore that upholds, that makes this true, that m is greater than n. So you got to be very careful here. So in this scenario, where d minus b is minus 7, that's fine, but you cannot get a scenario where c is equal to a. So these 9 will not count. So the only thing you can do is this 3 for the d minus b, and this 4 for the c minus a is 5. So that makes me get another 3 times 4, which is 12. Okay. All right, we're getting there. Painstakingly, but we're getting there. Okay, so next scenario. Going back to this equation here, that one up there. I'm actually going to write it again because I need to. So we have 7 times 11 times 13 times c minus a. And then we have plus 2 times 5 times 11 times d minus b. And that is equal to 5 times 7 times k. Another scenario that will be valid is if we set this time d minus b equal to 0. So we had d minus b equal to 0. This whole thing will vanish. And therefore, we would be able to make it work if c minus a equaled, let's see here, 5, I think. Yeah. Any other scenario? 0 and 5. Yeah, I think that's the only one that works. Yeah. Okay. So that d minus b equals 0, you can get, if you look back here, d has 10 possibilities, and so does b. So there's 10 possible ways of getting that. And then c minus a equals 5. Well, we've done that already. There's 4 possible ways of doing that. So then we get another 10 times 4, which is 40 ways of getting these two scenarios together. And I believe we're finally done. So the grand total would be that 27 plus 12 plus 12 plus 40. And that is what? 27, 37, 39, 51 plus 40. 91 is the answer. Suppose that p at x is equal to qx to the power 3 minus rx squared minus sx plus t for some positive integers q less than r less than s less than t, which form an arithmetic sequence. Show that x equals 1 is a root. X equals 1 is a root. So p at 1 would be 0. We have to show that p at 1 is 0. Okay. Well, they told me that these variables form an arithmetic sequence. So, an arithmetic sequence is of the form a plus d, a plus 2d, a plus 3d, like that. Where in this case, I believe d is greater than 0. Okay, so then let's plug that into here and let's see what we get. So p at 1 would be, first of all, q minus r minus s plus t, if we just plug in 1 for the value of x, correct? And then now let's plug in for each of these guys, these values. So p at 1 would therefore be q, which is a minus d minus a minus 2d plus a plus 3d, correct? So we have a plus a, so the a's cancel. And minus d minus 2d is minus 3d plus 3d is 0. So there we go. We just showed that p at 1 is 0, therefore 1 is a root. X equals 1 is a root. Part B. Suppose the average of q, r, s, and t is 19 and that p at x has 3 rational roots. Determine the roots of p at x. Okay. So q plus r plus s plus t divided by 4 is equal to 19, according to what they've told me. So let's plug in these values, these guys, right? The values that make them an arithmetic sequence. So it'd be a plus d, a plus 2d, a plus 3d. And that's divided by 4 is equal to 19. So if we add this all up, it becomes 4a plus 6d is equal to 4 times 19, 76. Divide through by 2, and you will get 2a plus 3d is equal to 38. And if we isolate for one variable, we get d is equal to 38 minus 2a over 3. Okay, I don't know how much that's going to help, but let's just see. Oh boy, now what do I do? I'm just trying to think, what direction do I go now? There is an idea of just plugging in these values into the original equation. Where's the original equation? And this is the original equation, right? And plugging in these values right here. But that's going to be some terrible algebra. Okay, let's just do that and see what happens. So when we do that, we get p at x is equal to ax to the power of 3 plus, minus a minus a plus d x squared minus a plus 2d x plus a plus 3d. Okay, now I think I'm just going to use this guy and get integer solutions for a and d. And I think that's the whole point of them giving us this. Remember that the average is 19. They wanted us to get a relationship between a and d. And they're positive. They're positive numbers. Let me just go back and double check that. Yeah, they're all positive integers. Okay, so we have to find integer solutions to this equation that give us positive integers. Okay, well, let's see. When a is 1, does it give us anything? When a is 1, we get 36. Yeah, 12. And then just keep going like this. When it's 4, you'll get another integer solution. 7 will give me 8. 10 will give me 6. 13 will give me 4, and then the last integer solution is 16 and 2, and then we start getting negatives. Okay, that's actually pretty decent. It's not too long of a list, so we can work with this. Okay, and then where do I go from here? So then I guess we have to plug it back into this guy. So then p at x, let's put p at x. For the first one, will be x to the power of 3 minus 13x squared minus 25x plus 37. You see how I got that? I just used this equation and then plugged in values for a and d, in that case a being 1 and d being 12. Now, we in part A had concluded right here that x was a root, correct? So if x is a root, that means one of the factors is x minus 1, right? If you factored this guy right here. So yeah, so after factoring x minus 1, this would give me, without the x minus 1, x squared minus 12x minus 37. Yeah. And then we have to figure out the discriminant. And the reason that is important is because something they mentioned in the question. If you go back right here, where is it? Yeah, 3 rational roots. So when do you have 3 rational roots? 3 rational roots would be, well, let me think about this. This polynomial is right here. It's a cubic, right? So the first root is x equals 1. And the second root, we don't know. We'll just call it root 2. And then the third root, I don't know. We'll call it root 3. Now this guy is already established. So that means that we have 2 additional roots. And they're rational. Rational meaning they're numbers. Like there's no roots. There's no root. Root is a terrible word to use because that's going to be confused. There's no square root. What I mean is, for example, there's no root 5, that kind of thing. They're numbers. You got it? So that means that the discriminant has to be, the discriminant cannot give me a radical. It has to give me a number. So that means the discriminant would have to be a perfect square. That's like, for example, you guys remember this is a quadratic. So when you find out the roots, you guys know the famous equation, x would equal minus b plus or minus the square root of b squared minus 4ac all over 2a, right? The famous quadratic equation. This is the discriminant right here inside the radical, this guy right here. And if that was, let's say we calculated and it's 5, then that would be minus b plus or minus root 5 over 2a. That's not rational. It has to be rational. See this word rational right here? So that means the only way it could be rational is if that discriminant is a perfect square. And therefore, when you took the square root, it would be a number. And then therefore, you'd get 2 additional roots. One would be the plus guy, the other one would be not the minus guy. Yeah, like this. You got it? So that's why the discriminant is important. So we have to figure out the discriminant, and we got to take the discriminant that is a perfect square. So let me just say must be a perfect square. Okay, so we got a little bit of work here. First, let me just write all these in instead of you listening to me write them in, and then I'll tackle the discriminants. All right, so we got all this in. Now the discriminant, we can figure that out pretty easily, right? It's b squared minus 4ac. So for the first one, for example, we're looking at these guys here. B squared minus 4ac. So it would be minus 12 squared minus 4 times 1 times minus 37, right? That comes to 292. In a very similar way, these calculations will be 644, 932, 1156, 1316, and 1412. But we want it to be a perfect square. The only one of those that's a perfect square is this guy right here. So that's the one we're going to work with. And what are they asking for? Determine the roots of, okay, so we got to find the roots. Okay, no problem. So the roots, using our quadratic, well, the first root we know is 1. That's been established in part A of this question. The second root, the next x2 and x3, I guess is what we're trying to figure out. So those roots, we get minus b from this guy right here. This is what the one we're using. So it'd be minus b, so minus 6 plus or minus. Well, the discriminant we already figured out, 1156 all over 2a, which would be 2 times 10. So this is 6 plus or minus the square root. 1156 is a perfect square. What is the square root of 1156? 34. So there we go. That's how we get rational. You notice how the square root disappeared? That's what they mean by rational. So this is 40 over 20, or minus 28 over 20, I believe. So that's either 2 or minus 14 over 10, which is minus 7 over 5. So therefore, the roots are the 1, the 2, and the minus 7 over 5. So this is the answer to the question. And as you can see, there's 3 roots, and they're all rational. There's the rational. There's no square root in any of those roots because we chose the discriminant to be a perfect square. Part C, prove that for every positive integer n greater than 3, there are at least 2 arithmetic sequences of positive integers, q less than r less than s less than t, with common difference 2n, for which p at x has 3 rational roots. Okay, so let's see here. N is greater than 3. n is equal to, for example, 4, 5, 6, and so on. And then the common difference is 2n, so d is equal to 2n. So Q, R, S, and T, these are the players. And then before I had set them as A plus D, A plus 2D, and A plus 3D, right? But they're telling me that D is equal to 2n, so then that's going to be A plus 2n, A plus 4n, A plus 6n, correct? Yeah. But, I think the algebra will be easier if I subtract 3 minus 3n. If I subtract 3n from everything, the algebra gets easier. So make this a minus 3n, a minus n, a plus n, a plus 3n. It's still an arithmetic sequence with a difference of 2n. So it's still valid. It's just by changing it like that, it just makes the algebra a little easier when I plug it into p at x. Okay, so now let's plug it into p at x. So remember, the same p at x, it's the same question, so it's the same guy right here. So, well, first let me write that down to, actually, wait, let me think about this for a second. Well, we actually found the roots, right? We found the roots in the previous question, and the previous question we found that this was the guy right here. So we are going to use these numbers for A and D. A is 10 and D is 6. So that means A is 10 and D is 6. So it's of the form 2n. So that means n is equal to 3. But n has to be greater than 3, right? That falls apart. So, but we can use that sort of as a guideline, even if that is not the exact case. So, for example, if we go back and look at that equation, this equation right here, and these two, we can use that as a guideline. So let's just use that as a guideline. Let's see what we get. When A is 10 and D is 6, we had the following equation. What was it? 10x 16 is 33 23. Okay, so it was 10x to the power of 3 minus 16x squared minus 22x plus 28. And then remember, we factored out the x minus 1 because x equals 1 is a root. So then that allowed us to get this 10x squared minus 6x minus 28. Okay, so that basically means if we compare coefficients, that this is a, so it's ax squared, this is d, so minus d x, and then 28, and 28 is what in terms of a and d. In terms of A and D, A and D, it'd be A plus 3D, I think, right? Because if A is 10 and D is 6, A plus 3D would be 10 plus 3 times 6, which is 28. So there we go. So it'd be A plus 3D. Okay, so then we want to put in the 2n. This is the one that we want to put in. So this is going to be A. I'm going to use these guys here. Yeah. So instead of A, I'm going to put A minus 3n. And then instead of D, I'm going to put in the 2n because that's what it's equal to right here. And then the A plus 3n. Yeah. Okay, I think that is going to work. And then, as before, we want to figure out the discriminant. because we have to abide by that whole thing that it has to be three rational roots. So the discriminant in this case, well, the discriminant is always b squared minus 4ac. In this case, if we look at that equation, that's going to be, well, I forgot an x in there, sorry. Right here, there should have been an x. So it would be minus 2n squared minus 4 times a times c like that. Okay, so let's do this algebra. 4n squared minus 4 times minus a squared minus 3an plus 3an minus 9n squared. So that's going to be 4n squared minus 4 minus a squared plus, hold on. No, this is a plus 9n squared. And therefore that's going to be 4n squared plus 4a squared minus 36n squared. And therefore oh yeah, there is like term. I thought there was no like terms. 32n squared plus 4a squared, and then we can factor this with the 4, and we'll get a squared minus 8n squared. Oh, this is discriminant, capital D. Okay, so that's pretty good. That's pretty good. This is a nice. It's not too complicated to work with. Now let's remind ourselves what the question is actually asking. So we've got a lot of conditions here. First, we have n has got to be greater than 3. Then there has to be at least 2 arithmetic sequences of positive integers and common difference of at 2n, and the 3 rational roots. Okay, so let's summarize those conditions on the side here. So the first thing is that we got to be able to find 2 arithmetic sequences. Okay, so that's the criteria, first criteria. Second is the difference has to be, small d, has to be 2n. And then the p at x has to have 3 rational roots. Okay, so let's talk about each of these. What do they mean, and how is that going to help us solve this? The question really is saying, show that there's at least 2 positive integers a. Okay, so this is the first part, 2 arithmetic sequences. So we have the first arithmetic sequence, let's say a1 plus d, a1 plus 2d, a1 plus 3d, right? So that's the first, and then they're saying there's another one. That'd be a2 plus d, a2 plus 2d, a2 plus 3d, like that. Show that there's at least 2 positive integers. Show, I think it's better if I write it out, that there are at least 2 positive, underline the 2 positive integers, a, of the form a, I guess, for which the rest is true. Got it? So the rest is true means the difference is 2n. Okay, so d is 2n. And there's 3 rational roots. 3 rational roots. Now, what does 3 rational roots means? It basically means what I explained in the previous part, that the discriminant is a perfect square. So d, big D, this guy, is a perfect square. And remember I explained that whole thing that if it's a perfect square, then the root sign, the radical sign would disappear, and therefore you would get a number that doesn't have a square root in it. Okay, am I covered all my bases here? Actually, I think I just a little bit, I'd like to put in that 2n. So a1 plus 2n, a1 plus 4n, a1 plus 6n, just to, just make this complete. a2 plus 2n, a2 plus 4n, a2 plus 6n. Okay, let me see if I've covered all my bases here. The discriminant has to be a perfect square, and we have identified what the discriminant is actually, so that's really helpful. 4 times a squared minus 8n squared. Common difference is 2n, we got that, and p at x has to have 3 rational roots, and we know what that means. It means that the discriminant is a perfect square. Okay, so we got everything set up, but now I have to actually solve this. So here we go. So let's try to keep this in the same screen as long as I can before I tackle this. Okay, so our goal really in this question is to come up with values that allow us to make the discriminant a perfect square. So the discriminant is this guy right here. So d is equal to 4 times a squared minus 8n squared, and we want that to be some perfect square. So this 4 is already a perfect square. So if this guy in here is a perfect square, then that will work. So we'll just call it k squared. So that basically means that this question is a squared minus 8n squared is equal to k squared. And we got to work with that kind of a scenario. Okay, so, and then, oh boy. Let me rearrange this a bit. I'm going to put the a squared minus k squared on this side. And I think that allows me to factor this 8n squared, the very simple factor of a minus k and a plus k. I think that might help. And then also, let's remind ourselves, which we had up here. Where is it? This scenario. These guys. Let's remind ourselves of that. And actually, I'll just write it. I'll write it again down there so that we have it. So we had Q, R, S, and T, right? And I had chosen a minus 3n, a minus n, a plus n, and a plus 3n, like that. Correct? And all of these were positive. I have to just double check here. Yes, all of them are positive integers. So that means that all of these guys are greater than 0. And this was just completing that inequality. Okay, so therefore, since this is true, that means that a is less than 3n, right? Or did I do that correctly? No, I did that incorrectly. Sorry. A is greater than 3n. Okay, all right. Okay, I don't know if that helps in any way, but I just wanted to fiddle around with those numbers. But I think the heart of it is this guy right here. Okay, this is going to allow me to figure out this question. So let's make a table and let's go with this, because we've got some work to do here. So we got the first factor, which is a minus k, this guy. Look at the second factor, a plus k. And I'm just going to put that a plus k is greater than a minus k for obvious reasons, because k is positive. All right. And then we got to figure out what is the value for a, what is the value for k. And then, yeah. And then from there, we can figure out some actual numerical values. So let's see here. So we want this to be we want integer values for a, right? Yeah, because remember, a is representing the first term. Yeah, as you can see, a is actually representing the value for q, and these are all, the q is a positive integer. So we want integer values for a. So let's just put here a is an integer, positive integer actually. Positive. Okay, so here we go. So keeping this in mind, let's see here. Yeah, that's an equation that we have to constantly refer to. If a minus k times a plus k is 8n, what are the possibilities? Well, you could have 8n squared and 1. You could have 4n squared and 2. You could have 2n squared and 4. You could have n squared and 8. You could have 8n and n, or you could have 4n and 2n. Now, because this is true, this is where we stop, because a plus k has to be greater than a minus k. Because you might think of other scenarios, but then that inequality would not hold true. Okay, so then we now solve for a and k. Well, a is just simple. You just add these two guys. You add this guy, and then divide by 2. So it would be 8n squared plus 1 divided by 2. Similarly, it would be 4n squared plus 2 divided by 2. And when we do, we get 2n squared plus 1. And similarly, we get n squared plus 2. We get n squared plus 8 divided by 2. And we get 9n over 2. We get 3n. And then the k's, the calculation would be the first guy plus the second guy divided by 2. Is that right? The first guy plus the second guy. No. The first guy. No, how you'd calculate k would be you take a plus k and then subtract from an a. So we have a and we have a plus k. So that's how you do it. For example, this would be 4n minus 3n, so that's n, like that. This is 7n over 2. When we do all the calculations, n squared minus 8 all over 2, n squared minus 2, 2n squared minus 1, and 8n squared minus 1 over 2. Okay, now, after we have all that, now we can see which one of these are positive integers. Well, remember, what is the definition for n? N is anything that is greater than 3. Let me just remind myself here. N, every positive integer greater than 3. So n is any positive integer greater than 3. Okay. So this would be not a positive integer. It would be a fraction. It would be divided by 2. Yeah, so, and then similarly this one and this one fails. But these two pass. Yeah. And also they're distinct. That's another key thing, that they're distinct. They're different. If you notice, no matter what integer you put in, you're going to get two different values. Okay, so let's see what we can get. Since n is greater than 3, let's just give one example. Let's try n equals 4. And when n equals 4, this guy, these two guys, the a and the k, for the first one, 2n plus 1 would be 33. And for k, it would be 32. And the next guy, n squared plus 2, be 16 plus 2, 18. and then it would be 12. So then if we created those QRST using the a minus 3n, a minus n, a plus n, a plus 3n, those guys, we calculate these out. Oh yeah, well, n is 4 for both of them. N is 4, right? So those guys, for each of these, let's see here. We're going to get 21, 29, 37, 45, and we get 6, 14, 22, and 30. And that satisfies this first criteria that we found two arithmetic sequences. The difference is n equals 2n. It's a multiple of 2, which I believe we chose 4. N equals 4, right? Yeah. And then the last criteria, this one, p equals 3 rational roots, is satisfied because the discriminant is a perfect square. But we need to first prove that. Let's see. Let's see if d is a perfect square first of all. D, according to our formula, was, where was it? Up here, right? 4 times a squared minus 8n squared. Or we had actually, we called it this right here. D is equal to 2 squared times k squared. So let's use that. That's a little bit simple. And since we have k, the d would either be 2 squared times 32 squared, which is definitely a perfect square because you can just factor it out. Or the second d would be 2 squared times 12 squared, which is of course also a perfect square. So there we go. We have shown one such example, and the example satisfies all the conditions that part C is talking about. That when n is greater than 3, we have two arithmetic sequences of positive integers, common difference is 2n, and they have 3 rational roots. So let's backtrack. 2 arithmetic sequences. Yep, we got this first one right here. Let me just circle it. That's the first arithmetic sequence. Here's the second arithmetic sequence. That criteria is solved. Difference is 2n, okay? Difference is 2n. N is, we chose it as 4, so the difference would be 8. And as you can see, the difference is 8. As you can see, as you go from one term to another, it's going up by 8. And the same thing with that one. And the last criteria is that the p at x has 3 rational roots, and what that really means is that the discriminant is a perfect square. And we showed that the discriminant is indeed a perfect square for both arithmetic sequences. An equilateral triangle is formed using n rows of coins. There is 1 coin in the first row, 2 coins in the second row, 3 coins in the third row, and so on, up to n coins in the nth row. Initially, all of the coins show heads. Carly plays a game in which, on each turn, she chooses 3 mutually adjacent coins and flips these 3 coins over. To win the game, all of the coins must be showing tails after a sequence of turns. An example game with 4 rows of coins after a sequence of 2 turns is shown. Below A, B, and C, you find instructions about how to refer to these turns in your solutions. If there are 3 rows of coins, give a sequence of 4 turns that results in a win. Alright, so what they first did is over here, they gave you sort of a definition of when you are flipping, that what to call that flip. So for example, as you can see, the first one is T11. That means you're flipping those 3 coins. And if you flipped another set of 3 coins, it would be called T21, that kind of thing. You got it? So I'll try to use that. So they basically want me to go from this, which initially they're all heads, right? So they want me to go from that eventually to all tails. And so that it would finally be like this. Is that what they're asking for? Let me just double check. If there, yeah, 3 rows of coins give a sequence of 4 turns. Okay, so let's see. 1 turn, 2 turns, and then 1 turn, 2 turns, 3 turns, and then 4 turns. Yeah. So let me put in the circles first, and then we'll talk about how to. So one turn, 2 turns, 3 turns, and then this is the 4th turn. 1, 2, 3, 4. Okay, so the first turn I'm gonna do is I have to flip 3 of them, right? So let's see, which one should I do first? Well, I mean, I think there's more than one way of doing this, so I'm gonna flip the middle 3. So these 3 I'm gonna flip. So that means this becomes tails, tails, and tails. So then the other ones remain heads. Then what am I gonna do? Then let's see. There's lots of ways of doing this here. I'm going to flip these 3 guys, and when I do, it'll become heads, heads, tails, and the remaining are heads, tails, and heads. Right? Okay. And then we're going actually here, the next one. Then I'm going to flip these guys, these 3. And when I do, I'll get heads, tails, 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 heads, and heads. And then I can flip these 3. And when I do, I've already drawn it out. Tails, 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 tails. Okay, now the important thing is they want me to use this kind of characterization. I can't just draw those arrows and say, well, there you go. So based on that, this move was T22. Let me just double check on that one. Yeah. And then the next move, I believe, was T21. The next move was T23. And then the final move was T11. Yeah. And I think that there's other ways of doing it, but I think there's other ways of doing it, but this is one of the ways, and it's perfectly sufficient. All right, let's move right along to part B. Suppose that there are 4 rows of coins. Determine whether or not there is a sequence of turns that results in a win. So we're going to need a lot of space for this one. Okay, so actually let me keep one of these guys let me keep that in the frame, because that's already 4 rows of coins, right? Yeah, that's pretty good to have it as a reference. Okay, so we want to basically show, if you have this 4 rows of coins, can we do a series of flips that results in a win? And a win is described as all of the coins going from heads to tails. Very similar to how we did it with 3 coins. See, initially it was all heads, and then later we made it all tails. Can we do that with 4 rows of coins? Okay. All right, so let's see if we have a systematic approach. We want the final result. And another good thing about keeping these guys in the screen is that I can just copy those moves. You know how they're written, T11, T22. I can just look at that. Okay, so if we want to get a scenario where we're taking everything from heads to tails, let's try to do that as quickly as possible. Okay, well, one thing I can see is that when we have these guys, right? Let me just draw them out first. If we were to flip the 3 coins, like that's one flip, this is a second flip, and then this is a third flip, then we'd be able to flip everything from heads to tails except for the middle coin, right? So those 3 flips, according to the nomenclature up there, is I believe T11. That would flip the top 3 to tails. And then the ones in the bottom left, that flip I believe is T31. That would make these guys tails. And then the 3 in the bottom right, that flip is it 3-5? Yeah, I think it's 3-5. And that would make these guys tails. So then the only one that would be remaining ahead is the one in the middle. That's pretty good. That's promising, but doesn't necessarily guarantee that this can be done. But that's, I would start with that. Can I keep this in the same screen? Well, I'll try to as much as I can. Now, actually, let me do this on the side here. There's something I need to explain, because the flips actually, when you flip something twice, it's kind of like the same thing. Let me explain what I mean by that. Let me describe a flip, and then let me just talk about it, and hopefully that will explain a little bit better. Let's say there's no flip. No flip, basically. 0 flips of 3 coins. Then we have basically a head scenario, right? That's how it originally starts. If we have one flip, one flip once, then this becomes a T scenario, correct? And then if you flip twice, then we go right back to head, correct? If you're doing the same coins. So what that means is that 0 flips and 2 flips give the same result, as you can clearly see. So this is 0 flips right here, and then 2 flips is right here. They get the same result. So that is very important to kind of talk about. Okay, so let's go back to our what we were doing. So we got here with these 3 moves, right? So that's pretty good. So now let's see what we can do. Can we make this work? Right? Okay. Now, since if we flip something once, we get a different result. But if we flip it again, we get the same result. So if we flip something once, that is the only way we can change it. Because if we flip it again a second time, it goes right back to the original. So the point I'm trying to make is that you will get the same result if you flip something twice. So it's pointless, because it's not going to help anything. So as long as you flip something once, that is the extent of the change you will get. If you flip it a second time, you go right back to the original. So far, we have used, let's see, what have we used? We've used this guy, 3-1, and 3-5, right? So we have the other 6 moves. Let's see what would happen if we implement all of the other 6 moves. If anything works. Okay. So let's try T21. And if we do T21, then we will flip let's see, we'll flip those three, so it'll be HHT, right? So it'll become HHT, and then everything else remains the same. T, right? Let me just make sure I did that correct. Okay, so then we took care of this guy. Have we won so far? No, we haven't. Okay, let's do something else. Let's try T22. Let's try this guy. T22. And if we do that, we get T, H, H, T, T. Okay, did we win? No. Okay, let's keep going. Let's try T32, which is this guy. If we do that, we will get a T, H, T, H, T. Okay, we still have not won. Let's see. Let's keep going here. Let's try this guy, T23. Because our goal, we want to use all of them at least once, and then we're done. When the final result is what we have as a conclusion. Because if we use another turn, it goes back to the same result as I had illustrated here. Yeah. So next one we can use is T23. So T, H, T, H, T. Okay, still have not won, because remember, a win is when everything is a T. Okay, next one. Well, let me go back to the diagram here. T23 has been used. Where's T23? Oh yeah, the next one, T33. Let's use this guy here. T33 would make it T, H, T. Still have not won. And finally, there's only one left, T34. T34, let's see, what does that one do? That makes it T, H, T. There we go. So even after using all 9 moves, so let me write that out. So even after using all 9 moves, the center coin, this guy, is still head, H for head, and therefore it's not possible to win this game with 4 rows. Now you guys might say, well, why don't you just keep going? Why don't you keep trying, have another, try this one again or try this one again? Because if you try something a second time, you're into this category, and it's going to be the same as trying it 0 times. And we've already gone through a scenario where we tried everything 0 times, right? Like, for example, if we got to this point, we had not tried this yet, so that had been tried 0 times. If you try it twice, it's the same as trying it 0 times, so the result is the same. So that's why this should be understood in order to kind of explain the conclusion. And that's it for part B. Determine all values of n for which it is possible to win the game with starting with n rows. Okay. All right. Well, Okay, so before we tackle this, let's just summarize what we found out so far in the first 2 parts of this question. We found out that when n is equal to 2 rows, can you win? Let's see, yes. Because n equals 2, that's just this kind of scenario, so you just flip it once, and it would go from heads to tails, right? It starts off as heads. You just flip it once. Let me just put that in. You flip it once, it would go to tails, and then you win. How about when n equals 3? Can you win? And the answer is yes. We did that already, right? We did that in part A. N equals 1. Sorry, n equals 3. Yeah, here was n equals 3. This whole thing. So we did that in 4 moves. Okay, so n equals 3. Yes. C, part A. Part 10A. Okay. And then n equals 4. Big long song and dance. And we said no. And that was C, part 10B. Okay. So that's actually pretty decent findings. And I think that's the foundation of what this will be. So let me insert some diagrams here. So these diagrams hopefully will illustrate what I mean, that the first 2 parts of this question kind of lead to this third part. Okay, so let's say we have a scenario like this, right? That scenario is going to be used with this finding and this finding. Yeah. So notice this is a diagram with how many rows is it? 1, 2, 3, 4, 5, 6, 7, 8. N equals 8 in this case. Well, actually, n could equal 5 if you only look at this part of the diagram. 1, 2, 3, 4, 5. Yeah. Then if you kind of extended it, it would be n equals 8. Now, both of these are guaranteed a win. You say, well, how do you know that so quickly? Well, think about it. This diagram, it's been broken up into groups of 3, groups where they have n equals 2 and groups where you have n equals 3. So for example, this top part is n equals 2, and then this guy here, that guy is n equals 3. Now each of those, if you worked with them individually, you could win, right? So let me write that out. Please note that the game can be won when n is equal to 2 or n equals 3. So work on each section. So therefore, work on each section of n equals 2 and n equals 3. As in parts 10A and 10B of this question. And as in 10, just 10A, not 10B. 10A is the one that we used for n equals 3. And then when n equals 2, you just flip it once, as I showed here. Yeah. So there we go. So that shows that you could do it for n equals 5 and n equals 8. And then similarly for every multiple of 3. So n equals 3. If you keep adding 3 to that, that would be, let me think about this first. 1, 2, 1, 2, 3, 1, 2, 3. Yeah, you keep adding 3, right? So n equals 11, and so on. So n equals 11, n equals 14. So n basically of the form 3k minus 1? Yeah, 3k. So if n is of the form 3k minus 1, you can win. And this is the explanation why. All right, so now let's turn our attention to the next guy, which is this diagram here. This, as you can see, is, well, it could be, if you look at the entire thing, it's n equals 9. But if you just look at the first part, it's n equals 6, right? In a very similar way, that can also be 1. So in the same kind of scenario, game can be 1. When n equals 3, as shown in part 10a of this question. And these are, if you look at this guy, it's just a bunch of n equals 3s if you subdivide it. And actually, no, there's a couple of n equals 2. I actually forgot that. Yeah, see, those are n equals 2. So very similar to what I wrote here. Those n equals 2 can be just flipped once to go from all heads to all tails. So a very similar explanation. So that means that you can win when n is of the form 3k. So we'll make a conclusion that if n is equal to 3k or 3k minus 1, game is winnable with a series of steps for n equals 2 and n equals 3. And those steps I've already described a few times actually. Okay, so now we say, okay, we got every number is of the form, every number is of the form either 3k minus 1 or 3k plus 1, right? Because 3, like for example, this is like an example would be 9. An example of this guy would be 8. An example of this guy, like if k equals 3, it would be 10, right? And every other number can also be, so you say, well, what about 11? 11 would be this guy. 12 would be this guy. 13 would be this guy. You see what I'm saying? Any number can be put in one of these 3 categories. So we've already proved that the game is winnable for these 2 guys. So 3k, winnable. So we'll put a W for winnable. So now we have to turn our attention to 3k plus 1. Can you win with 3k plus 1? Okay, so let's see. So here is a diagram for 3k plus 1. So n now in this diagram equals 3k plus 1. In particular, it is 1, 2, 3, 4, 5, 6, 7. N is 7. So I guess k equals 2. Is that right? 3 times 2 is 6. 6 plus 1 is 7. Okay. So we have to now see if this is winnable. Now each group of 3 can be labeled 1, 2, 3, and that's how this is labeled. So each group of 3 is labeled 1, 2, 3, right? And all of those can be flipped just once and you can win. So at first it seems, okay, it looks like everything could be 1. But if you notice, there's going to be one guy in the remaining. So this group flipped, win, this group flipped, this group flipped, this group let's see here, this group 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Aha, see, it doesn't work out as perfectly as you hoped. So to kind of show that in a kind of a mathematical way, I'll just explain. When you have a 3k plus 1 scenario for the number of rows, there will always be an additional coin labeled 1. Labeled 1. So the total number of coins is going to be 1 plus 2 plus 3, right? Here we have 1 coin, 2 coins, 3 coins, right, in each row. There's 3k plus 1 rows, so it'll go all the way up till 3k plus 1. Got it? And when you add that up, it's going to be 3k plus 1 times 3k plus 2 all over 2, and that is the total coins. Let's move this up. So if you do this math, this is going to be 9k squared plus 9k plus 2 over 2, and that is actually 9, if you factor out a 9, k squared plus k over 2 plus 1. And if you, whatever that is, it's going to be an integer, right? Because k is an integer. This k times k plus 1. Yeah, so this is 2 consecutive numbers, so one of them has to be even. So therefore, this whole thing will be an integer. So we'll just call it t. So that means the total coins are going to be some multiple of 9 plus 1. And that's important because multiples of 9 really are multiples of 3. So it's kind of like 3 times 3t plus 1. So you're going to have multiples of 3, and then you'll have one additional coin. So you will be able to win with the multiples of 3, right? You just flip them once if it's possible. But you will always have one extra coin. That's what this is. And that will not allow you to win, which will not allow you to win. So therefore the conclusion, I'll just stay in the same screen, is that when n is equal to 3k plus 1, right? Is 3k plus 1? Yeah, and when n is equal to 3k plus 1, a win is not possible. So going back to the original question, what were they asking? Let's see. Determine for which values of n it is possible to win. Okay, we discovered that it is possible to win when n is equal to 3k or n is equal to 3k minus 1, but not possible to win when n is equal to 3k plus 1.